So better not to keep a space in between. So I've downloaded 3 times. Let me just remove. Okay. So this is the file I've downloaded from the PDB database. Okay. So now I have a folder, and inside this folder, I have kept the file that I've downloaded from the PDB database. Okay. And this will be my working folder. So all the files that I'm going to create, and also all the files that. All right, so this is the interface of, I can open it. So this is the interface of Autodock tools. Let's open the file, this one, right? It is in, for me, it is in E drive, and in this folder, and under this folder, again, one more folder, right? Day one, this is my working folder. And inside this folder, we have this file, right? So let's open this. So if I click here, file, and hit the read molecule, it's going somewhere else, right? So if I have to open my file, I have to go to E drive, then this folder, come to day one, and then the file, right? It's a long process, and we are going to create several files. So if I going to navigate something like this every time, and also while opening the file for the final run, if I'm going to navigate all the files like this, there will be a might be a chances for you creating an error later on. Okay, so what we can do is, just to save time and also to avoid error, we can set the path of this working folder, I mean this workspace or this particular tool, to our working folder. That means if I click open and read molecule, it will directly land into my uh, working folder here instead of navigating. Okay, so we can set the path of our working folder in this software. So just open your working folder and click in the address bar, and then copy the path of your working folder. In the address bar, you can just do a right click and then copy the path of your working folder, right? And then come here and then go to file again, and go to preferences and click here set. This is optional, it's not required or compulsory, but it saves times, and also it helps us to avoid mistakes or error later on. Okay, so better to set the path of your working folder, the folder that I'm going to generate files and import files. Okay, for my docking, set the path of this working folder to your software. Okay, so if you go under this startup directory, you just, here we have copied the, from the working folder, we have copied the address, right? So whatever address, for in your case, you just copied it and paste it here, right? So once you paste it here, you make this as default. And now you can dismiss this window. And if you go to the file again and you read molecule, it should land in directly to our working folder. Okay, so now we can access working folder easily. Just click the file, select the file, and click open. Right, this is the structure. All right, this is in different representation. We are not concerned about representation for now. So you go to this window, particular window. Okay, this if you go under this window, you have this all molecule, and under this current selection you have this triangle here. Okay, in your case, if you have used install the latest version, it will be a plus sign here. Okay, so it's the same thing. So you just click the plus sign or the triangle here, then it will expand and show you what are the chains present in this structure, right? So remember, we said that we are going to keep only chain A. Chain B is the same, which is the this particular another chain. Okay, so it's a homodimer, so I'm going to delete one of the chain. And C and D are some sugar moieties, right? So those are also not required, so I'm selecting all those that I do not want to use it for docking. Okay, so I'm keeping the chain A unselected, right? Why I'm selecting? Because I want to delete all this. So how do you delete? Once you have selected what you want to delete, go to the edit menu here. Okay, go to the edit menu, click the edit menu, and under this edit menu you have another option called delete. Okay, so go under the delete option, and there is something called this delete selected atoms. So it's very intuitive. Only whatever you want to delete, you select the those molecules first. So this S means selection, and this is first column is for selection. So whatever chain that you want to delete, you select it first, right? And then go to the edit menu. So there will be a delete option. So under this delete option, you have the delete selected atoms. Okay. So when you click this delete selected atoms, there will be a warning window. It's saying that once you delete this, you cannot undo it. That's okay. So just click continue, and you see that the structure that we have selected are all deleted, right? Yeah, so if you join the second day session, you will be getting the certificates, as well as we have this tutorial in PDF. Whatever I'm showing here, step by step, we have also tried to present here in PDF format, so that uh, if you are beginners, obviously you won't be able to do this in one go. Okay, so you have to keep on trying, and to make it easy, the process or the journey for molecular docking using Autodock 4, we have tried to put our best effort to keep it in a PDF format step by step. So I mean, you can refer to this also, and then you can also look at the recorded video, and you can try it, okay, at your own pace. Anyways, so if I come back to my workflow, you see we have removed unnecessary chains that are present, right? That were present. And let's remove the water. Fine. So if I zoom in, I don't know if you can see or not, but there are dots present here. These are red dots are the water molecules. Okay. So these are the water molecules. So I want to delete the water molecule. So if you go to the edit menu here, there is uh, a separate option for deleting water. Just you have to click here, delete water. Okay. Now the next step is to delete water. So in order to delete water, you go to the edit menu again and click the delete water option here. Fine. So the water is now gone. It's been deleted. So, and then if I go to the in this workflow again, I had to add polar hydrogen and then assign charges. We can add polar hydrogens, but better if we uh, do it separately. Receptor separate and ligand separate. Okay. So now what is left? If I expand this, this is chain A. Okay. So if I expand this, I think in small molecule section, some nitrate and ethanol are also there, right? Nitrate I already deleted, I guess. This is in chain B, T, and L. Okay, some alcohol moieties were this also we deleted. So some alcohol moieties are also present. So if you just expand this chain A, okay, if you expand the chain A, you can see the residues of chain A, glutamate 4, and all everything is present. Okay, so if you scroll down, these are the amino acid residues. Okay, so if you scroll down, and at the end you can see the E20 is the uh, yeah, E20 is the donepezil, right, the drug molecule. So you have E20 and EDO is there. So what is EDO? EDO is the alcohol moieties, right? Some alcohol moieties are present. So we need to remove them. So remember, whatever you want to remove, you just select them first. Okay, select the EDO. Two EDOs are present. So select them both and then go to the edit menu and go to delete and click the delete selected atoms. Okay, and then click continue. Fine. So what is left is the receptor, the enzyme, and the drug molecule, donepezil. Only these two are left now. Okay. So before I proceed, I would like to save this. Okay, this is a checkpoint. I think I have gone too fast. So let's go to the file, save, and click the write PDB here. Okay. So we'll be saving this in PDB format. And here change the name. I'll call this as ACHE E20 or something. Only these two are present right now. So it is in PDB extension, okay? So ACHE underscore E20 dot PDB. So I'm saving this structure after removing or processing all the files or all the molecules or chains that were present. I'm saving this structure, okay? Only the receptor and the ligand. Just click OK. And then in our working folder, we can see a new file here, right? So this file contains the receptor and the ligand only. Fine. So now I can proceed from here. So I can delete the ligand and keep uh, only the receptor, because in our process, you see, you have to separate the receptor and the ligand. But then if I follow from here, uh, I mean, it should not give any error. It should be, uh, okay to go forward. But then it's a free tool and it has many bugs. So if I follow from here, it's giving me error when I try to convert the receptor into PDB-QT format. So let's avoid those errors and try to save time. Okay, so let me restart this file or restart this software. Okay, don't get confused. Okay, I'm restarting this because in my system or other system that I have tried, if I proceed from here, okay, uh, ideally it should work, but then in the step for in during the step for converting the receptor into PDBQT format, it is giving me error. Okay, so let me just exit and restart the steps again. I mean, restart from this particular step again. So again, it's important to save this because sometimes the software may crash. Okay, so if you do not save this file or this checkpoint, okay, then you have to start from the scratch again. You have to delete all those things. So better if you keep on saving the checkpoints, you can, if the software crashes also, you can come back to the steps where you have left. Okay. All right. So let me open the receptor and ligand only file. And then from here, I need to delete the ligand because I want only the receptor before I do the polar hydrogen addition and also assigning the charges. So this is the ligand or the drug molecule. Now I want to delete this. So because I want to delete this, I'm selecting the drug molecule, and then I have to go to the edit menu, same procedure, go to the delete option and then click the delete selected atoms. Okay, here's the same warning dialog. Just click continue and it has deleted the ligand. So now I can add the polar hydrogen and then assign charges. Okay, so go to the edit menu again. I need to add hydrogen, so I need to search where something hydrogen is there. Okay, yeah, so hydrogen is there. So under this hydrogen option there is add option again. Okay, go to the add option, and here in this add hydrogen window, we can see that all hydrogen you can add, and also you can add polar hydrogen. Keep these methods and all default and then click OK. So I repeat again, you need to add polar hydrogen. So if you want to add the polar hydrogen, or to make it simple, okay, so if you want to do manipulation of the structure, any manipulation, whatever, add polar hydrogen, delete water molecule, add charges, whatever manipulation if you want to do, you always have to go to the edit menu. Okay, so go to the edit menu, search for hydrogens, and then go to the add hydrogen, add this option, and then in this window you select the polar only and click OK. That's it. Okay, so again, adding charges, here you can see we have to add or assign charges. Adding charges is also kind of manipulation that you want to do with this structure, right? So whatever manipulation you want to do, if the process is to manipulate your structure, go to the edit menu, search whatever the manipulation that you want to do. Again, here is the option for charges. So under this charges option, you have this Castinger and then Coleman. Okay, so according to the manual of Autodock 4, they mentioned that Coleman charges is optimized for macromolecules like receptor, DNA, etc. Okay, so you just select the Coleman charges here, and Gestinger is for small molecules. Okay, so for now, let's select the Coleman charge and click OK. Fine. So we have added the remove unnecessary chains, removed water, added polar hydrogens, then we have assigned the charges also. Okay, so this is done. So our receptor processing is done. Now we need to convert this into PDB-QT format. So PDB-QT format, its conversion is unusual in this uh, Autodock tools. So we'll keep it for now like this, and when the when we do the next step, we'll be converting this into PDB-QT. So directly we cannot convert. So there is a step that we need to finish first. So after that, we'll convert it into PDB-QT format. Okay. So for now, let's keep it as it is, and let's focus on the ligand. So from our workspace, from this structure, we have already deleted the ligand. Okay, ligand is not present here. So what we can do is we can go to our folder, and remember here in our folder we saved the receptor and the ligand. Okay, so let's open this in any text editor. Sorry, yeah, in any text editor. Okay, and if you scroll down at the end, this is the amino acid residues. Okay, this is the amino acid residues, and here from here it start the small molecules. Okay, small molecules, which is they are represented by het atoms. Okay, heteroatoms. So this is E20, right? If you see, we have E20, right? So E20 is the drug molecule. It is present in chain A currently, and this is the number. Okay, and what this represent is the Cartesian coordinate. That means x coordinate, y coordinate, and z coordinate of this particular atom, carbon atom number 1 in this drug molecule. Okay, so we need to copy all this information starting from this first atom till the last atom of this drug molecule. Okay, so let's copy this. Simply just copy. Okay, first atom till the last atom, or copy all the information, right? Select all the information, then copy it and open a new file, paste it there. Yeah, so this is the information, right? E20 for starting the first carbon and the last atom, which is also a carbon, right? 28. So let's save this file, save as. An important thing, you need to change the save as type. Now it is in text format. Okay, I don't want this in text format. I'll keep it as all types so that I can save this in PTB format. Okay, so I'll type here ligand.ptb. You can give any name. I'm just giving this as ligand.ptb. Okay, change the save as type to all types and give any name and save this into PDB extension. Okay, and click save. So if you open the working folder, you find a new file called ligand.pdb. So basically what we have done is we have extracted the ligand file or the ligand molecule from the PDB structure, from this PDB structure, which contain the receptor and the ligand. Okay, so we have the ligand separate, we have the receptor separate. We already processed the receptor. Now let's process the, sorry, now let's process the ligand. For the same for ligand, we have just followed the same procedure. So let's open the ligand. Okay, so let me hide this receptor. We're not going to use this for now. So so this is for hiding. Okay, you can just open, click here, and then see the visualize whatever structure is present, or if you want to hide, just click again. Okay, so let's open the ligand here, file, read molecule, and ligand file is there. Click open. So this is our ligand file or ligand structure. So same procedure. I want to add polar hydrogen if any place is there for adding the polar hydrogen. So if you go to edit and then go to hydrogen, add, right? Polar, click OK. That's okay. There is no place with that polar hydrogen. And if you go to charges, you go for compute Gastinger. Okay, small molecule, you need to add Gastinger charges. Click OK. So you can add polar hydrogen and Gastinger from here, or otherwise you can directly open from this option also, menu also, inner menu, where there is a ligand written here. Okay, so from here, if you have opened the file from here, that also okay. If it is there in the workspace, we have to use this ligand option in the inner this uh, menu. Okay, so go to the ligand here, ligand option here, go to input, and since the structure is open in the workspace, we are going to use choose. Okay, if the ligand is not open in the workspace, you have to click open and navigate to the folder where the ligand is present and then open it. Okay, since it is already open in the workspace, just click choose, and from the list you select the ligand and then hit the select molecule for docking. Okay, now it's giving a summary for the ligand. It's saying that it's already added the Gastinger charges, found 15 aromatic carbons, and also detected 6 rotatable bonds. So it has set the torsional degree of freedom of this ligand molecule to 6. Okay, so click this OK. So we can change the rotatable bonds, but let's not do it here. It will complicate the process. So just go to the ligand again and go to the output and save this as PDBQT. Okay. So I'm giving the same name, but the extension is different, so it will be easy to differentiate. So I'm just keeping this as ligand.pdbqt. If I go to my working folder, I get a new file called ligand.pdbqt. All right. And if you see our workflow also, we need to convert this into PDBQT, right? So we have added the polar hydrogen, nothing was there. Sign charges, sign number of rotatable bonds. We kept the default 6 rotatable bond were there. And then we have converted the ligand into PDBQT format. Okay, so all right. So what next, right? So let's keep it this PDBQT conversion little bit, okay? Uh, it's coming, okay? So, but let's keep it here for now. So next thing is we have to define the binding site, okay? Placement of the region where you need to do or you want to do docking, okay? Placement of the grid box. We call it as a grid box. It's very important, okay? So manually we can place the grid box, but it's if you are able to place it optimally, okay, just covering the active site pocket, not making it bigger. And if you are able to place the grid box at the center of the active site pocket, okay, just covering the active site pocket region, then you call it as optimally placing the grid box, right? So how you can do that? And again, for this particular example, we will be able to do optimal placement, but this is not universal. Okay, sometimes I'll explain again later, but sometimes uh, your protein or the ligand might not be in this kind of position. So in that cases, this process may not work that I'm going to do. Okay, for now it will work. Why? Because you see, this is the active site pocket. Okay, this is the experimental one. So I have shown this here in the surface view. Okay, so you can see that this is forming a nice channel. So this is the one. Okay, this forms a pocket, and this pockets kind of form a channel. Okay, this is the active site pocket. So you see, we have to place a grid box covering only this active site pocket. Now, for this grid box, there will be a center of the grid box. And also, we can adjust like how big the box will be. Okay, dimension of the grid box we can change. So how to place it optimally is, you see in this, you can see that Doni Pijal is nicely fitting inside this pocket. Okay, that means it is I mean the length of this channel, the Doni Pijal is fitted right from the starting till the outlet, right? So, so I mean from the starting to the terminal, right? So so if I'm able to calculate the central point or the center of this Doni Pijal or the drug molecule, center point will be somewhere here. Okay, somewhere here it will be. So that means it will also be the center point of this active site pocket. Okay, so if I'm able to put the grid box center here, I will be able to enclose the whole active site region for docking. Okay, I don't want the grid box to be large. I don't want to grid box to be small to left out the active site pocket. Okay, so to optimally place, it is always better to find the center of the active site pocket. So in this case, since the co-crystallized drug molecule is spanning the length of the active site channel, if I'm able to calculate the center of this drug molecule somewhere here, and then I will be able to place the center of the grid box here. And then once you place the grid box, I will show you. Okay, don't get confused, just telling you that why we are going to calculate the center of this uh, drug molecule. Okay, so that we can get the central point somewhere here. And then once you get a central point here, we'll be placing the grid box center. Once the grid box is placed, center is placed here, I will be able to select how big the grid box should be, okay, to enclose the whole active site pocket. All right, so what we are going to do next is calculate the centroid of the drug molecule, okay? So let me open this in any text editor, and you can see here, this is the x coordinate, y coordinate, and z coordinate of this atom number one, which is carbon. Okay, so similarly these are all the xyz coordinate of the corresponding carbon, I mean the atoms present in the drug molecule. Okay, so if I am able to calculate the average of this x coordinate, y coordinate, and z coordinate, that means I will be able to get the center of the this drug molecule. Okay, central point of the drug molecule. So let's calculate the average of x coordinate, y coordinate, and z coordinate. Just copy this, and you can use Excel for this. Paste it in the Excel. And then data, let's format this properly, right? Go to data, text to column, next, and finish, right? So this is the x coordinate, y coordinate, and z coordinate of all the atoms, corresponding atoms, right? So I want to calculate the average of this. So if you want to calculate the average, if you have to go to home, and there is the function to do that, right? And if you list out all the functions, you have the average here. Okay. So click average and press enter. So this is the average value of this x coordinate. And if you drag this, you will get the y and z coordinates. Okay. This is the averaged value of this x, y, and z coordinate. That means we have just calculated the central point or centroid of the drug molecule. Okay. Again, just to clarify, we are calculating this centroid to get the center point of the active site pocket so that we can place the center of the grid box. So here we have processed the receptor, we have processed the ligand. Now the next step is to placement of the grid box. Okay. Since we are going to do targeted docking, we need to place the grid box properly to cover the active site pocket. Okay, optimally cover the active site pocket. So there is a menu here called grid. So just click the grid here, and there is an option here for macromolecule. So when we generate this grid box, or again, we have to generate grid map also. Okay, so first we have to define what is the receptor that we are going to use. And also you have to tell the software that this is my ligand that I'm going to dock. Okay, so if you go to the grid, go to macromolecule, and since the receptor is open here or the macromolecule is open here, you go for a choose option. Select the receptor and click the select molecule button. That's okay. So when you click OK here, you are now will be able to save this in the PDBQT format. Okay, the process is unusual, but yeah, this is the process to save the receptor in the PDBQT format. Processed, I'll call this as process ACHE.pdbqt. Okay, save this. So we have defined the receptor, and in the process, we are also able to save this in the PDBQT format. Now we have to define the ligand. Okay, so go to grid again and go for this set map types and go for this choose ligand, because ligand is already open in the workspace, right? So go for choose ligand, and from the list you select the ligand and hit the select ligand button. Fine. And then now again go to the grid, and here is the grid box. Okay, when you select this grid box option, a box will be present here. Okay, so this is the grid box, or this is the enclosure where we are telling the software that we want to do in this particular enclosure only the docking process, the searching, calculation, everything. Okay, so you can change the direction and try to place this manually. So you can do like this, but then it won't be proper. Okay, so what you can do is, we have calculated this coordinates, right? So if I place this x, y, g centroid of this coordinates, x, y, z coordinates of the drug molecule, and place in the grid box center, that means I am making the centroid of this drug molecule as the center of the grid box. Okay, so let me show you what I mean. I'm trying to say, I'm trying to tell here. See, there is a star here, yellow star, which is the center of the grid box. Okay, so I want to place the center of the grid box at the center of this drug molecule, because the drug molecule is spanning the whole region. Okay, and you can see that it will be also the center of the active site pocket. So if I keep here minus 14.108 minus 43.83 and then 27.6